Welcome back. In the last episode, we wrapped up lower winds with real-world techniques for takeoff and landing. Now we climb to higher altitudes to explore the dynamics of upper winds, how they form, how they move, and why they're so important for flight planning. Let's begin with the basics. Upper winds are high-altitude winds typically found above 5,000 feet, extending up through the troposphere. At these levels, friction from the ground no longer slows the air down, so wind speeds increase dramatically. What causes these upper winds? The same force that drives surface winds, pressure differences. But in the upper atmosphere, the pressure gradient is broader and the Coriolis effect is stronger, leading to faster, more uniform airflow. When the pressure gradient force and Coriolis effect balance out, we get what's called geostrophic wind. These winds flow parallel to isobars, without turning toward high or low pressure. This is the standard pattern at high altitudes. Above about 2,000 feet, this balance becomes dominant. That's why upper winds don't angle into pressure centers, they circle them. Pilots flying at cruising altitudes must understand these flows to optimize fuel and avoid rough conditions. Let's introduce the jet stream, one of the most important upper wind systems. Jet streams are narrow bands of fast-moving air in the upper atmosphere, typically found between FL 300 and FL 400. They flow west to east and influence everything from routing to turbulence. There are two main jet streams, the polar jet and the subtropical jet. The polar jet is stronger and more variable. It's found at mid-latitudes and often dips or rises depending on frontal systems. The subtropical jet is smoother and more consistent. Jet streams form at the boundaries of air masses with strong temperature gradients. Warm air to the south, cold air to the north. The greater the contrast, the faster the wind. That's why jets can reach over 200 knots in winter. These high winds don't just impact speed, they affect routing and flight planning. Airlines often ride the jet to save fuel on eastbound flights and avoid it on westbound routes to reduce headwinds and delays. Let's apply this practically. Flying from New York to London, the jet stream may reduce your flight time by 45 minutes. But returning west, you may have to fly a longer but more efficient route, staying out of the core flow to reduce fuel burn. The jet stream isn't a straight line, it meanders like a river. These bends are called troughs and ridges. Troughs dip southward and often bring unstable weather below. Ridges bulge northward and usually indicate calmer, drier conditions. These patterns change daily, which is why pilots check upper wind charts, significant weather charts, and winds aloft forecasts before every flight. Knowing the jet stream location helps with turbulence avoidance, ETAs, and fuel management. Turbulence is a major factor near jet streams. The edges, especially where wind speed changes rapidly, are zones of clear air turbulence, CAT. These areas may be invisible but can be severe, especially at night or over oceans. To avoid CAT, pilots look at wind shear gradients on upper wind charts. A change of more than 40 knots over 1,000 feet is a red flag. If encountered, pilots often climb or descend 2,000 feet to exit the zone. Let's talk numbers. Jet streams typically occur around 30,000 to 39,000 feet. Speeds range from 80 to 200 plus knots. Strongest during winter, when temperature differences are highest. Weaker in summer, with flatter pressure gradients. Now, how are upper winds measured? Through radiosondes, weather balloons, and satellite observations. Aircraft also contribute via automated reports, feeding into real-time weather models. The data is compiled into tools like FD wind and temperature charts, upper air prog charts, jet stream forecast models. These give wind direction, speed, and temperature at various altitudes across your route. Pilots use these to decide optimal cruise flight level, when to change altitude for smoother air, where to adjust route for headwind or tailwind advantage. Let's run a scenario. You're flying from Paris to New York. The jet stream core is centered over the North Atlantic at FL 360. Your dispatcher suggests FL 340 to stay beneath it on westbound legs, reducing turbulence and fuel burn. Another example, a transcontinental flight in the US uses a high-altitude ridge to cruise at FL 390. Favorable upper winds provide a 25-knot tailwind, shaving 20 minutes off the ETA. Passengers are happy. Dispatch is happy. Fuel use is lower. Win-win. Let's not forget the jet streak, a segment of maximum wind speed within the jet stream. These can create divergence aloft, which encourages rising air and storm formation below. That's why upper winds are critical in forecasting severe weather. Jet streaks also affect pilot workload. Passing through one may bring light chop or altitude changes. Understanding the structure of the streak helps reduce surprises in flight. Now, let's link upper winds to aircraft performance. Headwinds equals longer flight time, more fuel. Tailwinds equals shorter time, less fuel. Crosswinds equals drift, needing heading correction. Vertical wind shear equals possible turbulence or speed changes. Performance planning must factor all of these in. FMS units today automatically adjust for wind data in cruise, descent, and approach phases. But pilots must still verify, especially when forecasts change en route. Let's talk about Mach number in relation to wind. As you cruise higher, true airspeed increases, but so does wind sensitivity. A strong tailwind can push your ground speed well above planned, while a sudden drop can affect time to top of descent. Modern aircraft can display wind vectors on the nav display, helpful for situational awareness. If you see strong crosswinds ahead, you might request a heading change or altitude shift to smooth out the ride. Let's wrap up this part with a checklist for managing upper winds. Review wind charts and jet stream locations before flight. Plan altitudes to take advantage of tailwinds or avoid headwinds. Monitor CAT zones and plan options for vertical escape. Use onboard wind data to adapt in real time. Stay flexible with routing and descent planning based on winds aloft. In the next episode, we'll continue with upper winds, part 2, diving into wind models, real-life tools, and how dispatch and pilots coordinate to manage winds across the globe. See you in Meteorology number 26, Upper Winds, part 2.